Hello, I am trying to regulate the sound. Um, Please bear with me for a second. Okay. Alright, here we go. So, this is the webinar for Pytorch. This is the framework that we are going to use for the rest of the nano degree. So, I have prepared a bunch of slides and I I'm gonna have to go over the slides mostly because there is no time to go too much into code. But if I can, did I go into some of the links to show you how it works in the notebook. Okay, well, the first thing that I want to talk about is the setup of the PyTorch library, which I have already done, and all I need to talk to you is about how to install it in a different environment so you can troubleshoot it easily if something goes wrong. It's very typical for Python libraries to get in trouble with different versions that are incompatible. So what you do is you create a conda environment. There are a couple of tools to create environments, but essentially this is an environment is just a directory in your hard drive where you can install. Oh, hold on, there is some echo here. I'm going to need to. Okay, that's it. So in this environment, you can install PyTorch, and then I have installed it here in one environment, and then launch the notebook in there. I'm going to briefly try to go and show you at least how activate. So here you're starting a new terminal, right? And let me just maximize. And okay, well, you can go conda env list and this show you all the environments that you have created. As you can see, I have created one for PyTorch here, and it's just a folder. So whenever I need to get rid of it, I just can remove the folder. Practically everything disappears and create a new one. And so if I want to use it, I can use the same conda tool, conda env, conda activate, and the name of the environment. And you can see that I am using that environment, which means that by default it's loading the libraries from this particular folder. So whatever I install now is going to go in there. So I think that I don't remember how I install PyTorch right now, but I think that you just go conda install PyTorch or something like that. You can look at the documentation in the same Udacity courseware. So what I wanted to show you is that I launched the notebook from here. So so you can go should be the notebook from here, and it will automatically load the PyTorch library in your path. So this is the way to launch it and to use an environment. Okay, so going back to the presentation, this is what I have listed here, essentially. Okay. The second thing that we need to talk today is Torch Vision. Torch Vision is just another library to help you with loading the data sets for images. So it's just here you have a functional way to compose functions which are called transforms, and then you apply this transform to the loader. So when you use Torch Vision, Torch Vision comes already with some predefined data sets. MNIST is the most common one, obviously. So you can specify your transform out here. So in this case, the transform is very simple. Just get the data and put it in a a Pytorch tensor, and then normalize the data. So each image is going to be normalized with with these parameters. That this means that the mean is 0.5 and the standard deviation 0.5. So essentially, after you apply normalization with these two parameters, you are going to have your images transform into something that is a lot easier for a neural network to learn from those images. So I think I have a link here to the notebook. Let's see if I can open this one up. So I just wanted to show you the thing running here. So it shows you that it has loaded batches of 64 images, which are one channel, so it's black and white, and 28 by 28. Now, here's where you specify that you want a 64 as a batch size. And you have another parameter here that if you set to true, it means that you want the training data. If you set to false, you'll get the test data set. So it just separates the data sets in 80% train and 20% test, or some percentage like that. So okay, I hope this is clear. As you pay attention to this, if this has to be only for one channel. If you put 3 times the value here, like for 3 channels, it's going to fail because MNIST is just black and white. It's just one channel. So back to the slide. If there is any need for validation, well, basically you're going to train with a train set, and then put it in a train loader enumerator, and that is going to load the batches one by one. You can do the same thing with the test data. Put it in a test loader here, so you can use it later for validation. All right. So today we are going to use Pytorch. So let's talk about Pytorch tensors. Tensors are just like NumPy, multidimensional arrays, and why we're using Pytorch instead of NumPy, because Pytorch automates the computation of the gradient. So that's a functionality called autograd, and it's also with Pytorch we have a convenient API to compute in GPUs, graphical units, rather than CPUs. So that can be done transparently. You just have to add the parameter GPU somewhere. And so the important thing is to, like in any vectorized software, is to learn how to manage the shape of the tensors. And there are several different methods to do it. And so here we have highlighted reshape and view. And here on the side I have, at the top I have some examples with a one-dimensional vector. So here's a one-dimensional vector or tensor, if 1, 2, and 3. And if you basically cast it to a one-column vector with a word view, so this function view, what it's going to do is reinterpret the memory into 3 rows and 1 column. And here you have a 2-dimensional vector with just 1 column. And Then reshape, it works exactly the same, um, uh, with the same parameters. Now you have resize too, and the difference between reshape and resize is that resize works in place. So the convention for Pytorch is that everything that ends with an underscore, like here, like resize, is going to work in place in memory. So this is for important for very big tensors, of course. So you don't, you don't copy memory around, and is important for small devices too. So, so as you see, the three commands they give you exactly the same output, but this is only because um, they are they are working on a very simple case. Now, if you take the example below, I have two rows, and I also showing another command transpose. So with transpose, you get exactly what you're expecting. So essentially, if you have two rows, 1, 2, 3, 4, 5, 6, you get two columns, 1, 2, 3, 4, 5, 6. So this is exactly what you expect. So in the case that you have to debug, you can also always resort to transpose. And transpose has different parameters. The parameters are not exactly the shape of the output, because transpose is an operation where the shape of the output is predetermined by the shape of the input, so you couldn't really override that. But it allows you to specify here is what dimensions are you going to transpose. So you're going to transpose dimension 0, which is the rows, with dimension 1, which is the columns. So in and going back to the ones that we saw before, view, reshape, and resize. View, reshape, and resize are, if you want, more physical. They work more at the lower level of physical interpretation of memory, while transpose is more logical. It works the way that you expect as a programmer. So if you look at the difference here, view, for example, is going to give you, yes, the same shape, but look carefully at the contents. The contents are different, right? So the first row, 1, 2, 3, is distributed in across the first row and the second row, 1, 2, and 3 below here. So it's not what you might have expected, that it was 1, 2, 3 in the first column. The same things with reshape, and the same things with resize. So these three work at the lower level. So what you can do in general is use transpose when you need to do something like that, for preparing for a matrix multiply, and then once your model works, you can use something more optimal like resize and see if it works. So if it doesn't work, it's because the way that your data is arranged in memory is not going to basically allow you to do it directly in place. Okay, so this about Pytorch tensors and how they are represented in memory and what operations you have to reshape them. I think that the other thing that you want to know is the operation that you are using with Pytorch tensors. And mostly the operation that you will be concerned on in deep learning is matrix multiply, and you have two methods for matrix multiply. As usual, the first one is simpler. Oh, Siri thinks that I'm talking to her. Okay. And the second one uses the with the second one you have broadcasting, so it can get a little bit more complicated sometimes when you're multiplying by a vector, and if you don't put the vector in the right position, it might work. The one that does broadcasting might work, but it's not going to do what you expect. So be careful with these ones. Um, don't have a link to the documentation, but I'm going to add one here so you can quickly see what is the difference. So the tensors in I like to help you to see where the tensors fit in this neural network graph that we usually talk about when we represent a neural network. So there are two ways to think about this. The representation way, which is a static way, the static view of the data. The feature vectors correspond to nodes. So we talk about feature vectors when we refer to the vectors that flow through the network from the input layer through the hidden layer and to the output. So the first feature vector is the input vector, and is represented here by these three nodes at the bottom. And the output of the hidden layer is another intermediate, if you want, feature vector, and is represented by these two nodes here. And we can interpret the tensor of weights. This is the tensor of weights here at the right, as all the arcs that connect the input nodes with the hidden nodes, and all the arcs that go to one of the hidden nodes are arranged in a column here in this matrix, in this tensor. And so you can consider that each one of these arcs is a scalar, which corresponds to a weight in the tensor that you're learning. And the computation of each one of these layers of nodes is dynamically. I mean, looking at this is you're going to see that each one of the layers just computes two operations on tensors, right? So you do the multiplication with the weights through and the previous layer, and then the activation. So each hidden layer is a product of a math multiplication and an activation. The input layer doesn't do any operation. You just got the input. So how do you use Pytorch to do a forward pass? So we're talking about a multi-layer perceptron and the simplest of neural networks. And the way we go about this is let's compute the first hidden layer, H1, these two. And it's not exactly H1, but it's H1 and H2 that you're computing here. Just use with the input vector, the features. Features here correspond to x1, x2, and x3, multiplied by W1. Now W1 is this whole tensor here. That's what we are calling W1 in code. And add the bias one. And the bias is not represented here. But it would be like nodes that are hanging out there without being connected to the previous layer. So then apply the activation and obtain the function f1, which corresponds to the output of the layer 1. And sorry, the names of these variables don't correspond exactly to the names paint in these nodes, but what I would have in this graph, if I could edit it, is f1 and f2 here. Or I could change the name of the variables too. So the second operation is just the operation that goes from the hidden layer to the output, and the is not represented here, the tensor, but this is a simple one-dimensional. W2 is a one-dimensional array, one-dimensional tensor. And finally, final activation on H2. H2 is a scalar. As you can see, it's just one number, and it gives you the output. So there are a couple of documentation links here that I am adding, and how to transform tensors from and to NumPy, and you can quickly review them later, but they are very straightforward. So my next slide is just a follow-up from the previous one. It's just how to implement the multilayer perceptron with what we call Pytorch modules. These modules are like classes that wrap up the tensors and support they support backpropagation automatically. So it makes it much easier to train neural networks, because you don't have to implement the backpropagation. So okay, the steps here are you can declare a class, a Python class, network in this case, that inherits from a module, and then you have all the things that come in module available for you to use here, like neural network linear. So this is a linear transform that takes 784 inputs and 256 outputs. So this is a matrix of these two dimensions, essentially, of weights. And this is going to be your hidden layer. Then you have another one for your output layer. In this case, we're processing MNIST data, so we want 10 dimensional output. We want an array of 10 elements, 10 scalars. Each one of the scalars is going to be the probability of the image being one of these digits. So that's a MLP approach to MNIST. Excuse me. Let me see if we have any questions. I'd like to know if somebody is online and want to let me know how am I doing. Do I have? Am I going too fast? Is my video and my audio coming through all right? Anything, you can just raise your hand and use the live chat in YouTube to let me know. Okay, so finishing with this slide, you can also use the functional API. Is pretty much a functional wrapper on the module API. So if you want to use the functional approach, this is when you usually when you don't want to define a class and do the other approach. It's just use a functional SF. That's a convention. And for example, here you have a function that defines the forward. Well, this is also in a class, actually. If you have cells here, it's in a class. But how do you the way that you call it is very similar. So you have f sigmoid here, and over here you have sigmoid that you have basically implemented somewhere else. So so essentially, functionally, you are programming a layer here by doing, okay, I'm going to compute the sigmoid of the hidden of the features, and hidden is what you have defined here. So functional allows you to write it this way, and otherwise you can also write it the manual way if you want, which is essentially you um, just compute the first operation and call it any name. For example, here is called x, and then compute the second operation, putting the first one as parameter, and reusing the same variable all the time, so don't need to make any mistakes there. It's very simple. Okay. MLP can be defined also with sequential. This is very similar to Keras. If you are familiar with that other framework, you can wrap all your operations in inside a sequential function, and that means that will take care of connecting them and feeding the output of the first one to the second one. Here I'm also using the ordered dictionary just to give a name to each one of the operations in memory. So in case of debugging, it's probably easier just to remember what each one of these tensors means. But without the order, just putting the list of operations here, it will work. So what the operations are doing is a linear transform. So this is a math multiplication of the inputs. Excuse me. And then apply ReLU activation, which is very commonly used in all the CNNs that we're going to see. So just another activation. As long as the activation is non-linear, you can develop the neural network with the same power of representing any function that you want. Okay, there is something here that we want to call your attention to, softmax. So our output is a softmax because we're classifying. We're going to talk about classification in the next slide. But softmax, what it's going to do is take the vector of 10 elements and essentially select the largest of those elements as a number that is close to 1, and all the other elements as numbers that are close to 0. So max is also like an activation function that is going to map a score, the input score, into a number that is between 0 and 1. So converting everything into a probability distribution. So here we talk about classification, the output function, and the loss. So the loss function is the cross entropy loss, which is a logarithmic function, and you have the right here the expression of the cross entropy loss, and essentially is a negative logarithm because logarithm of probabilities are all negative, so we negate to get a positive loss. And then the sum for all the output classes, so this will be the sum of the over all the digits. So you know the output classes for MNIST are the digits from 0 and 9, so here you can sum over all the digits of the multiplication of the label, so y is the label times the log of the probability that your system computed. So essentially your label is going to be, the way that we code the labels is 0 for all the digits that are not corresponding to the image, and 1 for only one of the digits that correspond to the image. So what happens here is that if your probability, let's suppose that your image was the number 2, so you're going to have a 2 label. We are going to have a label that its value is 1 in the position of 2 in the output array, and if the probability that you have computed for that position is close to 1, the logarithm of 1 is 0. So you're going to have a very small number here. You're multiplying very small number by 1, which is the label, and all the other labels are 0 for all the other digits. So the only loss that you're going to have is this very small number. So it means that whenever you compute the right probability, you get a very low loss. And when the on the other case, if you have a low probability for the correct number, say for the number 2 you have a low probability, this log is going to be a big number. It's going to be a big negative number because the log of 0 is tends to infinite, minus infinite, and then you negate it, and then you end up multiplying this large number by 1 and negating it, and you end up with a large loss. So that's why minimizing this loss is going to give you learning to minimize this loss is the correct thing to do for your network. So this is how you code it. You have a neural network cross entropy loss, put it into a variable called criterion, and then call criterion with the logits and the labels. So logits is just another name for scores, which means the raw output of the last matrix multiply. So the matrix multiply that computes the output layer before applying any softmax or anything. This is just the raw logics. And we're going to get into why you use the raw logics and not the output of the softmax, which are the probabilities. So this P here is the probability. This is the output of the softmax. But in reality, we just compute it directly from the logics. So okay, this is about the classifier output, and the other part of the slide is classifier loss, and this is the loss, and the other part is the output. So the output, we're using softmax, and softmax is this function right here, and is the essentially when you have an output that is y sub I, this output is a score. It could be a negative number or positive, and when you exponentiate, you just elevate the number e to that number, you always get a positive. So that that means that you can convert it into a probability. You need it to be positive, but you need it to be between 0 and 1, and you also need that all the probabilities that you compute add up to 1. That's the minimum thing you need to call it probability, right? So so that this formula is going to give you numbers that basically satisfies those conditions. So this is the softmax. You apply the y's here are your scores, and when you apply this formula to your scores, to your 10 scores, in this case, it's going to give you a distributional probability over the 10 digits. You can also use log softmax. I think that that is what is recommended in the lesson because it gives better results. It's a little bit more. So the log softmax is simply the after computing the softmax, applying the log. Here's a slide that goes a little bit more into the detail of the implementation of the cross entropy loss in Pytorch, and it essentially what it goes into is, okay, we are going to, if you look at this, we're going to compute the softmax, which is an exponential, and after computing it, we're going to apply the cross entropy loss, which is a logarithm. So if you put this formula, this exponential, inside here, because this is essentially the same thing, the POC is the same as this exponential here. So you see, well, the log and the exponential can cancel each other because they are inverse functions, so we can save some computation and save some error also. So that's what this formula means. So when you apply the loss to x and the class is the index. So you have to apply that formula, the exponential formula, and the log of that. You can actually remove this numerator from the log and from the exponential too. So I hope this is making sense to you. If you have any questions, please let me know. The chat is open, and this is just for your information. You don't have to do anything with this in the example in your project. You just use either cross entropy loss or the other loss that is going to be recommended into this one below here, which is the negative low likelihood. So okay, so I said that there is something called autocrat, which is a function in Pytorch that to automatically compute the gradients. Here is a little example taken from the lessons, and essentially, if you define a tensor here, 2 by 2, apply an operation to that tensor, another operation, and then compute, use the backward the function that is the way in Pytorch to compute all the backpropagation. So computes all the gradients. Now you can print the gradients and see what they look like, and and then compare it with what the actual value of the gradient should be. So mean, for example, here you're computing a gradient of mean, and mean is going to be basically it's going to divide by the number of elements, so you end up with the gradient is going to be divided by 2. Essentially, it's going to be the input value divided by 2. There is another way to compute this and see that they are the same, right? So all is showing here is that, okay, look, with backward you automatically compute the gradient. See, this is what you computed, and this is the right gradient, or the other way around. No, this is, yeah. And here's a comparison between the two, and it gives you 1 in each element, so that means that all the elements are the same. So hey, I'm ready to show you how to do training, prediction, and validation, which are the 3 things that you need to do in the project, and everything with Pytorch. So for training, here you compute and showing you the essential part is where when you are defining your model, you define your criterion. Here using the neg log likelihood. So negative log likelihood. This is pretty much what you can see here is negative, and is the log, and is the likelihood of your data, because it's the multiplication of all the probabilities. So when where was I? Training. Okay, yeah. All right. So when you define your criterion, then you can define an optimizer. There are several optimizers. Here is the simplest one, the stochastic gradient descent, and the optimization module in Pytorch contains several. One very common one is Adam. For this simple example, the stochastic gradient descent was fine. We have the optimizer takes as parameters the model parameters. So this contains all the weights in your model. If you have two tensors there, all the weights of those two tensors are passed to the optimizer function. So the optimizer function knows where are the numbers that it has to update in every time that you train an epoch. The learning rate is passed here as parameter 2, and then you have your these are very typical for a double loop, one for each epoch. An epoch is a full run on your training data. And then another internal loop that executes once for every batch. And train loader knows that it has to give you batches, because when you define it in Torque Vision, in the Torque Vision slide, you will see that you define it with batches of 64. So what train loader will give you is here two tensors. One is going to contain the images, 64 images, and the other is going to contain 64 labels. The first thing you do in this simple example is flatten the image. So you go and use the view transform, the view function that with the parameters that are 64 here. This is the first element in the shape of the image, and when you don't bother saying the rest, just compute it for me. This is plus -1, and it's going to compute 784. So you get images here are flattened, 64 rows with 784 columns each, and we use this because we are not using convolutions. If we were using convolutions, we don't flatten the images, of course. Just use the locality on both directions in convolutions. So the first thing you do is reset your gradients in the optimizer, because you compute gradients and average them for every batch. So after the end of the batch, you could continue using the same gradients and averaging more data, or just computing them from scratch for the next batch. And this is what we do here. And then compute the output. Just run your model function on the images, the flattened image here. So you will compute the whole batch, and your output is going to be a matrix of 64 rows by 10 columns. Remember, you want 10 columns because it's the probability of each one of the 10 digits. Then you are going to run that through the criterion function. The criterion is going to compute your output against the labels. Now the labels, imagine, is 64 rows. Each row contains only one column, which is the digit essentially that you want. So so essentially it's going to compute the loss, and actually the labels are going to be probably expressed already in one hot encoding. So each label, instead of being just one column with a digit number 2, is going to be 10 columns, and for example, if you wanted the digit number 2 is going to have a 1 in the position 2. So that's a one hot encoded label versus output, and then you are going to compute all the gradients with backward. Just a backward pass is as simple as this. It computes it for you, And finally, here's where you optimize the weights. So those weights that you pass to the optimizer step function is going to just update them for you with the learning rate. Everything is done. Now, finally, once you finish these two loops, your network is trained. So you can use the model to predict for any new image to give you the distribution probabilities of what digit may be contained in that image. So that's how you do it here. You call the model with the image, and you get the log probabilities. Remember that you were using log probabilities. So when you have log probabilities, so you have the logs of the probabilities. What you need to do to get the probabilities is to exponentiate it. So you just put it in an exponential, and you get the probability distribution. The probability distribution over 10 digits. So now you can do with this whatever you need to do. For example, you can transform, you can do the argmax. So you will have here vectors of 10 probabilities for your image. So you want just to find out which one is the maximum one. We'll see some ways of doing that in the validation part. So validation is the third step that you do here to see if your model is working correctly. So recapping, after training, you can do the prediction with an image that you didn't use for training. So these are one of the test images, and figure out if the prediction was right, comparing with the label of the test image. So here's the validation part. Essentially what you need is to read the test set from the same data set. This is the part that we already saw in Torch Vision, the Torch Vision slide. And you'll have them in a test loader. So test loader is going to load batches of images that your model never saw before during training. And now you're going to just select one of the different metrics for validation. So in classification, if you want a metric for the performance of your classifier, you can use accuracy. Accuracy is the most common one, and it's simply the ratio of number of correctly classified images over total number of images that you have in your test set. So accuracy is a number between 0 and 1, hopefully closer to 1. And the second one is prediction and recall. This one is more professionally speaking. You have to admit that your classifier is never going to be perfect, right? So you're going to be always doing a trade-off between precision and recall. Depending on the case, you can think, okay, well, precision is more important than recall, or vice versa, depending on what you are doing. The definition of precision and recall are, well, precision is from all the output of your classifier that is positive. Every time that your classifier tells you, okay, you are going to do a dogs classifier, for example, and say binary classifier, is easier to see this in a binary classifier. Every time that your classifier tells you, hey, in this picture there is a dog, so how many of them actually do contain a dog, right? So if your classifier is very precise, every time it says it's a dog, there's going to be a dog for sure. If it's not precise, it might just cry wolf or cry dog in this case, and there is no dog in there. Recall, well, recall is the opposite, right? This is the two types of error that a classifier can do. In one, it could be imprecise, and the other, it could have low recall. So low recall means that of all the images in the dataset that actually do contain a dog, how many did your classifier was able to identify, to recall, to basically, how many of those did the classifier detect? So in some cases detection is important, in other cases precision is important. It depends on the application. Uh, Top K error rate is another simpler metric. You just don't apply to classification very often. It's more like a metric for ranking. So when you have a, for example, Google search something, search for a keyword, and it returns 10 results. How many of those 10 results are relevant? 3, 4, 5, all of them. So that gives you an idea of the relevance of the quality of your model, but it's not for classification. I don't see it used for classification so often. I guess you could, but in this case, we're going to use we're probably going to compute accuracy anyway. So let's talk about have a couple of comments here of what you're going to do. Let's open the inference and validation notebook and load the data. Here is a simple it's a simple model that contains how many layers? 3 layers. So from the input image to 256, from 256 to 128, 128 to 64, 64 to 10. So you have 3 layers. Here are the layers computed, and once the model is defined, you just define the forward pass. You see, you don't need to define backpropagation. So create a model, and let's get something from test loader and run the model, and see what you get is probabilities. So the probabilities have the shape 64 rows by 10 columns. So of course this model is not trained, so the probabilities are going to be a little bit random, yes. But here's showing you to use the function top K, which you just use it to select the maximum probability. So you're saying, okay, give me the maximum probability. So let's say I get the probability of the image 0. So here's the distribution of probabilities in the image 0. They're practically all the same, 0.1, right? So as you can see, the model hasn't been trained, so the model is not sure about anything. So it tells you, okay, well, this image could be 0 with probability 110, or 1 with probability 110, or any digit with probability 110. Hey, you know, if you haven't trained me. What the function top K here is going to do, if you apply to this distribution of probability, is going to you pass 1 here. You're saying, okay, give me the top one across the dimension 0. Well, because I selected here only one row, there is only one dimension, is the dimension 0. So it gives you, okay, well, here's the biggest one, the 1997, okay, and it corresponds to the position 5. Okay, this is totally random, but it's just to show you that with this you can have the probability, the maximum probability, and the index in that vector of the maximum probability. The index is what you want. You want to know what digit had the maximum probability. So once you apply this now to the tensor, to the output tensor that has 64 rows, so you're going to get a column array as output, and in each row you get the digit with the maximum probability. Here's the 5 that was in the first row. This is, yeah, they all look like 5 and 6 because remember the output is random, the model hasn't been trained yet. So, okay, here this time it's all 7. So, this is the 7 one. Okay, now I guess there are some more tensor operations here. Okay, well, this is what you do. Once you have the output, that is the digits, and you want to compute the accuracy of your model, you say, okay, now if I compute the quality of this column array against the labels array, that's going to give you 1. Give me 1 when it's true that they are equal, and 0 when it's not true. So that's what it does here. It says, okay, top class is this tensor here, and labels is what you know from the data set that the digit is. And if you compare it here with the quality and assign it into an array that is equal, sorry for clicking, shouldn't be clicking here. You get this array that is a column array with 1s or 0s. It's computed here, and I actually want to see it, so let's just see it. It's going to be probably 0s most of the time, because just by random you would, yeah, that's right. So you have a 1 there because you hit it by random. It's actually I think is expected that if you randomly try to guess 10 times, you guess 1 right? Because you have 10 elements that is equally probable. So anyway, the accuracy is computed here with a mean. So essentially, if you compute the mean of this array, because they are all 0s and 1s, essentially you are computing the accuracy ratio. So how many do you actually got it right, which are the ones, divided by the total number of test examples. And you got 7% right. Yeah, as I said, the expectation is that you get 10%. Now let's see if you train the classifier actually. So let's add a loss, an optimizer, Adam, and works exactly the same. So 0 the gradients, and load the images, apply the criterion, and off you go. So let's see how this works. It's going to train for a little while. Remember that there is 3 layers in this one, so it's a little bit slower. And in the meantime, I can move on to show you what do we mean by this. So in this loop, if you compute the value of the training loss, so the loss is the function that you have defined here, and you can compute it on the training data and on the test data in each pass at the end of each epoch, and you then plot it here with the epochs at the bottom and the loss on the vertical. So you plot the 2 losses. The blue one is the loss on the training data, and the orange one is the loss on the test data, the unseen images. And you see how these 2 functions evolve, how these 2 losses evolve as your training progresses towards the 30 epochs. That gives you useful information of what to do, how to tune your system, so to tune your training. So essentially, what the blue one almost always behaves this way. it consistently progresses towards smaller and smaller losses, but that means that your weights are being optimized to predict those images. But the second one, the performance on test images, is the one that you are most interested of. The performance in test images here is reduced up until 10 epochs, and after that it actually starts to increase. What happens is that at 10 epochs your network has learned whatever it was going to learn about the data set, and the rest of the time is just memorizing the training data set. So this is called overfitting. You don't want this to happen. Basically, your network is learning to predict the training data set very well, but it doesn't know how to predict anything else. So any image that never saw is not going to predict it well. So essentially, it's learning quirks and things that are not relevant in the training data set. So little, distortion or noise in the shape of those digits. It's learning to predict those very well, but only those that are in the training data set. So what you need to do here is think why does it happen? Well, first it happens because the network has a lot of capacity. It has a lot of weights, so those weights can start modeling all the little quirks of your data beyond the essential features. So one thing you can do is reduce the number of weights. Just don't learn so many weights, because obviously you are learning things that you shouldn't learn. And another thing you can do is what we call regularization, which is done very efficiently with dropout. Dropout, what it's going to do is that in every epoch or every batch, it's going to zero some of the units, some of the neurons. So essentially, those weights are not going to take part in that particular batch. And so what is going to happen is that the other weights are going to, so you're just going to use half of the weights, and you're going to learn to predict with half of the weights, and then the next batch you're going to use the other half of the weights, and by the end, when you use them to train, you'll have 2 or 3 or n sets of weights that they can predict correctly in the same network, and they are going to become sort of an ensemble. So they're all going to predict together, but the output is going to be more or less the average of all of them. So you're going to get much more regular output. So and in that case, what all your weights are going to be applied to learn features that are important, and they generalize to the other data set, the test data set and everything. So and my training is almost done, and we'll see how overfitting works here. I have to watch the time too, so I would like to hear back from you guys if you have any question. If you are looking at this webinar online and you have questions, please go to Slack and send me a comment. I hope you can use part of this to your dog breed classifier project, because next week we're going to talk about about that, about the project details and how to go about that. What time is it? Is yeah, I'm 5 minutes over time, so I'm going to stop here. I would like to have time to talk about transfer learning, but I think that we have enough to digest here with Pytorch, and uh, we can talk about transfer learning one-on-one or in another webinar if we have a chance. So with that, thank you very much for tuning in, and let me just see how to stop this. Okay, so I'm gonna stop screaming, streaming. Send me your comments and send me your questions. I hope to get in touch with you this week, and that you keep working on the classifier project.